Geometry, lesson 11.4. We'll be talking about proportional partitions, and this will be the first of the videos for 11.4. So, we've been looking at triangles that have parts that are proportional, and now we're going to talk about triangles that have lines that are parallel. So we'll be renewing some of the properties that we learned with parallel lines and with transversals. So triangle ABC is similar to triangle ADE, and we've seen this type of triangle just a little bit ago. It shares angle A. Both triangles share angle A, and they have the characteristic of their bases being parallel to each other. So DE is parallel to BC. Sorry, correct that right now. This is true by AA, angle, angle, similarity postulate, because corresponding sides of similar triangles are proportional. It can also be said that AD is to DB as AE is to EC. Now, instead of comparing the left side of one triangle with the left side of the other triangle, or the right side of both triangles, or the bases of both triangles, we're now actually talking about pieces of triangles because of these parallel lines. So let me say that again for you and draw a picture so that you understand this. AD will be in proportion to DB, and AE will be in proportion to EC. So we're comparing the left side of the large triangle to instead of comparing the left side of the large triangle, we're just comparing the left side of the small triangle to the piece of the lower piece of the left side of the large triangle. This leads us to a theorem that shows how the parallel segment divides the sides AB and AC into the proportional parts. This theorem in 11.4.1 is called the side splitter theorem. It technically splits the sides. So a segment, and the segment they're talking to would be DE, parallel to one side of a triangle, and they're referring to BC, that intersects the other two sides, and they're talking about AB and AC. So BC and DE intersect the left and the right side of the triangle. Once it does that, it divides those sides into proportional parts. So not only can you use these parts in a proportion, you can state that angle B is congruent to angle 1, and we'll do that right here. So angle B is congruent to angle 1, and angle C is congruent to angle 2. Now this is because they're corresponding angles. So think of DE and BC as parallel lines and AB being a transversal, and that would give us these two angles would be corresponding angles. And the same thing goes for transversal AC. Sets up these two angles, angle C and angle 2, to be corresponding angles also. So there's a proof in your book about the side splitter theorem, and I'm actually going to go through this proof, but very slowly, just so you can see how they set it up. So, triangle ABC is similar to triangle ADE. So ABC, the larger triangle, is similar to ADE. And AB, the left side of the triangle, and AD, the left side of the right triangle, equal AC, the right side of the large triangle, and AE, the right side of the small triangle. Now this is part of the proof. This is how they're going to prove that the pieces can be in proportion. What we're going to do is use substitution to say that AD plus AB in proportion to segment AD is the same as or equal to AE plus EC in proportion to AE. So what they did is substitute, and let me go back to the last slide. We had AB and AC on top, which are the full side lengths of the large triangle. Now they've divided them into the actual sections. Now we're going to go ahead and place AD under each one of those sections, as you can do in math. And we have 4 fractions, 2 sets of proportions. Now we have AD over AD plus DB over AD, and let me show you where that came from. Remember, this was AD plus DB. You can take this AD on the denominator and you can separate this into 2 fractions, and that's what we've done. We have AE over AE plus EC over AE, and we did that by substitution, and you should be able to recognize that AD over AD and AE over AE are 1. So we now have this set of proportions. If we subtract both sides by 1, or subtract 1 from both sides, we now have this final proportion, which is what we were proving for, which is DB over AD is EC over AE. Now, we're saying this portion right here, DB, over the portion of the small triangle on the left side, is equal to EC over the portion of AE on the right side. And that can be compared to the original proportions that we stated at the beginning of the proof. And if you look at them, you'll see that this new proportion is actually inverted or flipped. And that's how they prove that this will work. Similar triangles justify the extended proportion, and now we've taken the same figure, but they just put variables in there. And this would probably be an easy way to keep the proportions in your notes so that you could work this. I would have a picture just like this to the right and have these proportions. So V to U is to U as X is to Z, and S is to T. So that's all 3 sides of the triangles. And V, X, and S are the small triangle. U, Z, and T are the large triangle. So we have left side, right side, base, being compared to left side, right side, base. Equivalent proportions and the side splitter theorem can be used to justify the following proportions. And out of this mix, you can get all 1, 2, 3, 4 proportions. And you could add these to your notes. And so for any of the problems that you're working, if you have values for some of these, you're going to look for values that you can use to solve your unknown. And if you have 3 values that'll fit one of these proportions, you can just substitute them in there and you can solve for your unknown. Here's example 1, and let's go ahead and do that. We have AD is 7.2 and DB is 4.8. We have AE is 10.8 and the unknown is EC. There are many proportions you could actually use for this, but they're going to use the original one they showed us, and they're going to place AD over DB, so this piece over this piece, and AE over EC. We substitute the known values and then we use algebra. So 7.2 EC equals 10.8 times 4.8. That equals 51.84. We divide both sides by 7.2, and EC is actually 7.2 meters. So fairly simple. The most difficult part of this will just be to set up the proportion properly. There's a converse to our theorem. This is a converse of the side splitter theorem. And if a segment within a triangle divides two sides into proportional parts, the segment is parallel. So this is the exact same picture, but what we've done is we've reversed the order of what we're solving for. And so 11.4.1 states that it's a segment parallel to one side, and that it divides the sides into proportional parts. But the converse says a segment divides two sides into proportional parts, so it is parallel. So one says it's parallel first and then becomes proportional parts. The converse says it's proportional parts and then it becomes parallel. So if you look at the notation down at the bottom, the 11.4.1 states parallel first. 11.4.2 states parallel last. Example 2. This is the same figure, it's just flipped, but everything still applies. And determine whether it's parallel, whether these two segments are parallel, XY and WZ. So we'll go ahead and set up some proportions, and they begin with the bottom and they say YZ is to ZV. There it is right there. And that you have numerical values, so that would equal 10 over 15, which equals 2/3. So to find out if it's parallel, the other side would also have to equal 2/3. So let's set up the proportion. It's XW over WV, XW over WV, which is 6/9, which equals 2/3. So yes, they are parallel to each other. We also have a corollary to the side splitter theorem, and if you take a look at this drawing, you'll recognize this. This is parallel lines and transversals. Now, if these lines kept going, this would eventually become a triangle. So what our triangle is just transversals that have met or intersected with each other. In this case, we're adding a parallel line. So it says 3 or more parallel lines divide transversals into proportional parts. So the same things apply. So P, this segment P, is to Q as R is to S. Now, these things will not apply to the lines that are parallel, but they will apply to the proportions on the sides. So let's work a couple of examples. We're going to find X. We have this figure. AD is 6 and DB is 3. AE is unknown and EC is 4. So let's go ahead and set up some proportions. And on the left side, we would have 6 to 3, and that would equal X to 4. And we'll cross multiply. 3x equals 24, and x would equal 8. So one of the things I wanted to tell you also is to test this. If x is equal 8, we could take a look at these two proportions, AD and AE, and that would be 6/8, which would reduce to 3/4. In your homework, problem 4b says complete each proportion. If AD is to DC, then AE is to EB, this piece. Very simple. And 5D, it uses our last, our corollary to prove, and it says W is to X plus Y as T is to, and your answer would be U and V. U and V. And don't let the fact that you have two variables being added here throw you. Just take a look at what the pieces are and line them up on the other side. Homework problem 8C. Determine whether EF is parallel to BC. They tell us, now this is a little different. You have to do some back solving. So we have BA is 10, and we have CA is 5. We know that BE is 4, so we need to solve for this piece, EA, before we do anything else. And if the whole length is 10, then EA is 10 minus 4, which is 6. And the same thing for this whole length. If CA is 5, then FA, or AF, will be 3, and our missing piece, FC, will be 5 minus 3, which is 2. So now we have our values, and we can set up our proportions. 6 over 4, or 6 is to 4, equals 3 over 2. And 6/4, if you were to divide both of these by 2, you would end up with 3 seconds. You could also multiply across. 6 times 2 is 12. 4 times 3 is 12. 12 equals 12. So it is, yes, they are parallel. Here's a last example. It's a little more complicated, but only because it's not a triangle. It's actually a quadrilateral. But these are parallel lines, so we can use these theorems. And we are asked to solve for RS if XY equals 2A and YZ equals 3A and the full length RT equals 15. So what we have to do is we need to get values in here on this side. And we know that this piece RS will compare to 2A. And you can see this in the proportion RS equals 2A. But we don't know what ST is. So all we can say is that ST equals 15 minus RS. So let me say that again. ST equals 15 minus RS. And that's what we can put in the denominator of our proportion here, our fraction. So you could write it as RS over ST, but ST is actually 15 minus RS. And that 15 minus RS will compare to 3A. And if you take a look at this, this proportion, those A's can be canceled out, and you could say that RS over 15 minus RS equals 2/3. So now we can go ahead and multiply across, and 3 times RS equals 2 times 15 minus RS, which is 30 minus 2RS. And we can add 2RS to both sides, and we end up with 5RS equals 30. And now all we have to do to solve for RS is divide both sides by 5. And RS equals 6. So hopefully this has helped. Here's your homework for 11.4a. Numbers 1, 2, 4, 5, 7, 8, 9, 11, 18, and 21. Be sure to contact me if you need any help. And we'll continue on with 11.4b in the next video. And I'll talk to you soon.